All right, Julapalooza number 2. Okay, so in this scenario, we got the car coming along. It has some initial speed given here, and it goes up, goes across a rough surface, all right, for 1.2 meters. Then it comes back down, but doesn't come down to the same height it started at. And then it hits a spring and it's going to stop. And what we want to know is what's the compression value over here of the spring. Okay. And so let's get some numbers on here. So we're starting out at, I know it says 6.5 here, but in my notes when I did it, I actually only used 6. So we're going to say 6 meters per second there. We're going up 1.5. We're coming back down 1. Okay. And so kind of the way we need to think about this is that from start to finish here, we've got a delta H there of just a half of a meter. Okay. So when it's all said and done, we're a half meter higher than we were before. All right. And that's what matters, is start to finish in this sort of thing, because I mean, we could try to find what's the speed here, then what's the speed here, then what's the speed here. We could do all that. That's a long way. That's the scenic route. Let's not do that. Okay. Okay. So here we go. Going to be a little messy again. Minus delta U G minus delta U E minus Q. Put in our equations here. 1/2 M V final squared minus V initial squared. And that's equal to minus mg delta H minus 1/2 K x final squared minus x initial squared. And we're looking for that xf value, the final compression for x. And then we've got some friction minus mu mg, we'll say delta x. Well, we should call it something. We're going to call this delta x. I'll call it delta x mu. I don't want to call it f because I don't want us to get confused with the friction, because I've got an x sub f on there. Okay. Well, anything we can throw away? Well, we know our final velocity term is 0, so that term's going to go away. We know that initially the spring is relaxed, so our initial compression term is 0 there. Okay, and that's all we get right there. That's all we get. Okay. Alrighty. So let's move some things around. So I want to move this term over to the other side. Okay, so we'll have 1/2 K xf squared. All right, and then we got minus mg delta H minus mu mg delta x mu. Okay, and then we can't forget about the 1/2 mv squared term there. So it's negative vi squared, so it turns into positive over here. 1/2 mvi squared. Okay, then we got to get rid of our 1/2 k, so we got xf squared, and we get minus 2 m over k g delta H minus mu m over k. Oh, 2, there's a 2 on there. Yep. Delta x mu. And the 2 cancels my half. I still got that weird m over k term. vi squared. Okay. Now, I mostly did this little trick here, m over k, m over k, m over k, just so it'd be easier when doing my calculation to keep track of things. All right, remember there's a lot of opportunities to enter wrong numbers and that sort of thing. All right, so by having sort of a repetitive thing like this, it's like a check. All right, I put it in every time and I'm like, oh yeah, I did that right. I did that right. All right, so put all those things in there. And so here's what it looks like when we get some numbers in here. Minus 2 And then I'm going to have half a kilogram over 300 newtons per meter, 9.81 meters per second squared. And my delta H is, I've gone up a half, so it's plus 5, and then minus 2 times 0.35. There's that weird term again, 0.5 kilograms over 300 newtons per meter. And we've got a delta XU, which is 1.2 meters. Okay. And plus am I leaving something out there? Yeah, that's what I thought. G, I need my G right here. I need my G. So I got to squeeze in a 9.81 meters per second squared. Okay. Sorry, I got messy on you there. I was going over the units in my head as I did this, and I was like, I ain't gonna work out. So I knew I'd made a mistake somewhere. Okay, 0.5 over 300. Again, we got newtons per meter, kilograms, and then this is VI, which is 6 squared meters per second. Okay, there we go, VF. Okay, so we got more of these weird units because of the newtons per meter squared, but I know this combination, kilogram meters per second, that's a newton. So those guys all cancel each other. So I got 1 over newtons there, and then I forgot to put my meter on there. So this whole first term turns into a meter squared, so that's nice. Again, kilogram meters per second, that's a newton, it cancels with that. And I got a meter. And I got a meter here, so that gives me another meter squared. And then same sort of thing with my last term in there. Anyway, what I'm going to get here is 0.0322 meters squared. Take the square root of the universe, and we get 0.179 meters. Okay. Just like so. Okay. There we go. So at this point, you're probably like, okay, and so they're all going to kind of be like this. Okay. There's not a lot of difference in these sorts of things. What changes is how high, how fast, what's the spring, what's the friction, all of those sorts of things change. Otherwise, they stay pretty much the same. I am going to do one more for you though. Okay.